Hey. So, again, I started recording and my video just stopped. And I never realized it. At least I realized it. Oh, see my babies? Look at them with Santa. My son looks thrilled, right? Anyway, I noticed before I finished, but I had gotten quite a bit in. So, today we're going to talk about tangent, normal, and binormal vectors. So, in this section, we want to look at an application of derivatives for vector functions. There's a couple of applications, but they all come back to needing this first one. So, in the past, we've used the fact that the derivative of a function is the slope of the tangent line. Well, with vector functions, we get the same result with an exception. So, given the vector function r of t, so this starts right here, given the vector function r of t, we call the derivative r of t the tangent vector, provided that it exists and the derivative does not equal 0. So, it cannot equal 0 if the tangent line to, so the tangent line to r, vector r of t at P is the line that passes through point P and parallel to the tangent vector, the derivative of r of t. So if r of t, the derivative r of t is equal to the 0 vector, then the vector has no magnitude. And so then we couldn't give us the direction of the tangent line. So it cannot equal, therefore, the derivative of r of t cannot equal the 0 vector. Okay, so also, so if if it exists and the derivative doesn't equal the 0 vector, then the unit tangent vector to the curve can be given by this formula here. And originally I'd forgotten to write the little vector, the ray over to indicate that it's a vector. So let me do that. So the unit tangent vector. So we said we call this the tangent vector. So the unit tangent vector is made up of the tangent vector and the length of the tangent vector, which is here at the bottom. So the unit tangent vector, so what the first problem says is, this is an example, so let's write example 1. Find the general formula for the tangent vector and the unit tangent vector to the curve given by this r of t. So, we start with finding the derivative, because this is the tangent vector. So the derivative of t squared sure is 2t. The derivative of 2 sine t is where the 2 cosine came from. The derivative of 2 cosine t is a minus 2 sine t. And so this right here is the tangent vector. So that's the general formula for the tangent vector. Now we want to find the unit tangent vector. So now we needed to have the tangent vector, then the magnitude or the length of the tangent vector. So we have this part. Now, if you remember, we're going to take the square root and square each component. So, looking at that, we start with writing the square root. So squaring the first component, that becomes 4t squared. Then 4 cosine squared t. And then 4 sine squared t. So now, hopefully remembering some things here, that cosine squared plus sine squared, or sine squared plus cosine squared, is just 1. So if you factored out that 4, you would have 4 times 1, which is 4. Okay, so now we have the length of the tangent vector. So we have both pieces. So now also note that this could be written as 1 over the magnitude times the tangent vector. So that's the way I'm going to set it up when I'm writing the unit tangent vector. So the unit tangent vector is, so I set this up, like I said, I have the length of the tangent vector multiplied by the tangent vector. So now we can take each component, we can take, this, the length of the tangent vector, the magnitude here, and we can, with a 1 over that, and we can distribute it within the parentheses. So doing so, this is what we're left with. And this is the general formula for the unit tangent vector for the curve. Okay, so our next example, we want to find the vector equation of the tangent line given by this curve. So we're right here, example 2. Find the vector equation of the tangent line, and we're given now what t is. So notice this is this is the same function we began with in example 1. So we've already found the general tangent vector. So we're going to take the general tangent vector and just replace t with pi over 3. So we want to find the tangent vector when t is pi over 3. So anyway, so as a reminder, this was 2t, so that's 2 times pi over 3. This was 2 cosine, so it's 2 cosine pi over 3. The derivative of 2 cosine was a minus 2 sine, so that's minus 2 sine pi over 3. Okay, so this is the tangent vector at t equals pi over 3. So the next thing we had to do was find the point on the line at t equals pi over 3. So this point on the line, we use vector r of t and plug in the pi over 3. So pi over 3 squared is pi squared over 9. So sine of pi over 3 was 1/2. No, sine of pi over 3 is half of square root of 3, so that becomes square root of 3. Alright, cosine of pi over 3 is 1/2, so 2 times 1/2 is 1. And so this is, we can create the point. So a point from here, we would have pi squared over 9, square root of 3, and 1. That's a point. And remember, from the origin to that point, we can form a vector. So to write the vector equation of the line, we're going to take the vector that comes from the point plus t times the vector here for the derivative. So 2 pi over 3 comes down. Well, what is 2 cosine pi over 3? Hold on. So when I did this earlier, I was looking at this. That's why I was getting myself confused. So this is where I got this from. So yeah, the sine of pi over 3. So sine of pi over 3 was square root of 3 over 2, which is where this square root of 3 came from. Now, for this, what we're multiplying by the t, we get from the derivative. So 2 pi over 3. Now, cosine pi over 3 is 1/2. So 2 times 1/2 is 1. Then sine of pi over 3, the sine of pi over 3, which we did earlier, is half square root of 3. And so 2 times half of square root of 3 is the square root of 3, and we use that minus. So this gives us the vector equation of the line. So before moving on, note a couple things about this example. So we could have used the unit tangent vector had we wanted to know the parallel vector, but that would have made a more complicated equation. So also notice that the vector r of t, we use that to represent the tangent line, despite the fact that we use that as well for the function. So the vector r of t is much like y in normal functions. So with normal functions, y is a generic letter we use to represent functions. Y, we always say y is the same as f of x back in, well, you probably were learning algebra, even before that. So the vector r of t tends to be used in the same way with vectors. So the next thing we want to talk about is the unit normal and the binormal vectors. So we'll look at the unit normal. So for unit normal, we are going to use an uppercase N, and of course, the vector, the ray for our vector. So the uppercase N of t. And so that we take the derivative of the unit tangent divided by the magnitude of the unit tangent. So I made this little note on the side. So the unit normal is orthogonal or perpendicular to the unit tangent vector. So that implies that it's orthogonal to the curve as well. So we've seen normal vectors when we were dealing with the equation of planes. This will show up regularly as we move through the rest of multivariable calculus. So the definition of the unit normal vector may seem a little different when you first see it, but it follows a theorem or a fact that I wrote, and so I'll show you. So this says, suppose that vector r of t is a vector such that the magnitude is equal to c for all t. Then the derivative of that vector is orthogonal to the original, to, you know, its antiderivative. So, we could do a proof here, but we are going to save that. We might be able to get to proofs later on, but if not, we prove a lot of the the calculus topics through theory of real variables and some other classes, you know, the first and second semester, because there's a whole year of that. Okay, so now we want to talk about the binormal vector. So this is when I noticed that it wasn't recording before. So we're going to start here. So the binormal vector, we're going to use uppercase B. So vector B of t is going to be the unit tangent vector, cross product, the unit normal vector. So, because the binormal vector is defined to be the cross product of the unit tangent and the unit normal vector, we know that the binormal vector is orthogonal to both the tangent and the normal. So, let's take a little note here. The binormal is, I'm not got enough room there, is orthogonal to both the tangent vector and the normal vector. And I'm going to put, that means perpendicular, which is orthogonal. So, example, I guess this is only really example 3. Alright. So, I'm going to type the question and then, you know, write the vector part. Find the normal and binormal vectors for why is this not, there we go. Okay, 4. Alright, vector r of t is equal to t sine t and 3 cosine t. Alright, so the first thing we want to do, is we want to find the unit tangent vector. So we want to get the tangent vector and its magnitude. So we need to get the tangent vector, and its magnitude. So, to get the tangent vector, that's just the derivative of what we have. So, the derivative of t is 1, the derivative of sine, and the derivative of 3 cosine. So pretty basic. We didn't have to do anything crazy. So the magnitude, and I do always like to use my notation. So this is going to be 1 squared, which is 1. Oh, I wrote this wrong. I wanted to do 3 sine t and 3 cosine t. So all I did now is I added the 3 in there. Let's do that. So you'll see why in a minute. You might. So now squaring, that becomes 9 cosine squared t plus 9 sine squared t. So because now these are the same, we can factor out the 9. We know that cosine squared and sine squared is 1 because we just talked about that. So that would become 1 plus 9, which is the square root of 10. Okay, so we have the tangent vector and we have its magnitude. So therefore, the unit tangent is equal. Alright, so remember that is 1 over the magnitude. So each component here is going to just be put over the magnitude. So we're going to have 1 over the square root of 10, 3 over the square root of 10 times cosine, and then negative 3 over the square root of 10 times sine. So I know that a lot of times we try to rationalize the denominator. We're not going to worry about that in this. So we found the unit tangent. So now the unit normal vector will now require the derivative of the unit tangent. So going back, so the unit normal, go back, let's see, where's the unit normal? So the unit normal is going to use the derivative of both of these. So we found, the unit tangent. So unit normal needs us to find the derivative here and its magnitude. Okay? So the derivative of a constant is 0. So the derivative of 3 over square root of 10 cosine t, you really just look at that cosine because remember you can slide the constant out. So that's going to become, cosine is negative sine, so negative 3 over square root of 10 sine t. And then negative 3 over square root of 10 sine. The derivative of sine is cosine. Okay, so that is the derivative of the unit tangent. And so now to find its magnitude, we're going to say the square root of 0. Then, I'm not going to even write that because the square root of 0 is 0 and it won't change anything. So now square negative 3 over the square root of 10. So that becomes 9 over 10 sine squared t. Then this also is going to become plus 9 over 10 cosine squared t. So hopefully you're seeing a little bit of a trend here. So the sine squared, cosine squared is 1. So that just leaves us the square root of 9 over 10 which is 3 square root over square root of 10. Not 3 square root of 10, but 3 divided by square root of 10. So we have all these pieces. And remember, it says find the normal and find the binormal. Oh, I didn't mean to. So, the normal, what we're looking for. And I'm going to, the normal vector. Normal is what we're looking for. The unit normal. That is going to be, so go back and look. That's going to be the derivative over the magnitude. So, derivative over the magnitude. So, you would just put each, the 0 over the magnitude is 0. So, now looking here, negative 3 divided by square root of 10. If I was to divide that, put that over, it was cancel. They would cancel, and so you're going to be left with negative sine t. And then when you take this last component and divide it by 3 over 10, you're left with negative cosine t. So that is the unit normal vector. And so the last thing it asked us to find, so this is the, hold on, this is the unit normal. So now the binormal, all my years in algebra, I want to call it binomial. Obviously it's not. We're not even, this is not what we're doing, but I'm so used to saying that. Now, the binormal vector is found, so I'm going to, because it's, it's way up there by this point. That is the unit tangent cross product the normal. Okay, so the unit tangent was here and the normal here. So we're looking at the cross product. So okay, let's see. We had 1 over square root of 10. Then it was 3 square root of 10 cosine t, negative 3 square root of 10 sine t. And the little trick that we did, back when we learned cross product, is to bring the other two out. And so then we had 0, negative sine t, negative cosine t, 0, negative sine t. Okay, so let me go slow so I don't make an error. So if we go here minus here. Okay, so that would be negative 3 over square root of 10 cosine squared t and then minus Okay, minus, okay, so the two negatives would make that a positive, which you'd still have a minus. So that would be 3 square root of 10 sine squared t. And all of that would be with your I, or, you know, technically, we could write this in like this. And we'll simplify that a little bit in a minute. So then the next part would be 0 minus this, which would become positive 1 over square root of 10 cosine t. Yep. And then the third component, I would have this minus 0. So this that I just said, that would be negative 1 over square root of 10 sine t. Alright, so we can simplify here because they have the cosine squared. Sine squared is 1, and then you could take out the negative 3 over square root of 10. So that would just be negative 3 over square root of 10, then 1 over square root of 10 cosine t, and negative 1 over 10 sine t. And so that is your binormal vector. Okay? So, with all of that being said, what we're going to be moving into is arc length with a vector function. So we're going to pull back, go back to, or we'll look at our vector, and we're going to look at two-dimensional parametric curves and the arc length, looking at getting arc length. So we'll have an arc length, get our integral for that, and some examples. And so, as you know, the midterms are due the Monday of spring break. So we won't have any more graded assignments for your midterm before the midterm grade is posted. But we will do an assignment when we get back from spring break that will encompass some of what we just did, and then also moving into the arc length with vector functions and curvature, then into velocity and acceleration. So I think it's going to be some fun stuff. So let me know if you have any questions, and see you next class.